Thank you very much. Thank you for the opportunity to talk today. So I'm going to talk about some exploratory and ongoing work on cargo capacity management, which I hopefully will convince you that it's an important class of problems. This is joint work with Andrea Lodi and our student Justin Dumouchelle. So let's see. So why is this important? So I think everyone is probably aware of parcel delivery is booming, in particular these days due to online retail. The market is in 2019 was worth like 430 billion US dollars estimated to, and over 100 billion packages, small packages were shipped in 2020, and actually it's forecasted to that volume will double by 2026. So there is a boom in parcel delivery, but at the same time there is a negative effect around this, in particular greenhouse gas emissions. So the transportation sector accounts for about 30% in the US, and I think that number holds for many countries. Also, the transportation is actually has inefficiencies. So a significant share of the vehicle miles traveled by trucks, for instance, are done empty. And I don't think I need to convince you about the cost associated. There's a huge cost associated with congestion. So this kind of motivates there is a need to improve the capacity usage, decrease negative and environmental impact of transportation. And part of this can be done through differentiation of services and prices. So we kind of have two fields here interested. On the one hand, supply chain management, interested in where we focus on managing the supply and the optimization of the supply. And on the other hand, we have revenue management that is focused on managing demand. So through structural price and quantity decisions. And this talk is going to focus on revenue management side, and particular quantity decisions, but related to cargo capacity management. So I think we're all kind of used to seeing revenue management on the passenger side when we're booking airline tickets, or in the days when we were actually booking airline tickets. And so we're kind of used to seeing this differentiation of prices and services on the passenger side, but it's actually not very well developed on the cargo side. It's less studied in the literature and less used in practice. And one of the issues is that it's kind of complicated to do cargo capacity management, in particular because the capacity is not as clear as in the passenger side. In the passenger side, one passenger occupies one seat and that's all. On the cargo side, capacity is typically defined in several dimensions, such as weight and volume. Typically, you don't know the actual capacity that is needed until the shipments are actually loaded. And also you have some nice flexibility in routing, right? So unlike a passenger who wants to get in a particular flight, you have some flexibility when it comes to cargo, which makes this for quite interesting problems. So what I'm going to do is that I'm going to give kind of a stylized view of cargo capacity management booking control problem. I'm going to discuss a bit about related work, so how it's solved in the literature right now, and then I'm going to present some exploratory work, some ideas around machine learning for combinatorial optimization. And we're going to discuss a distribution logistics application and some result there, and before some concluding remarks. So here is a very stylized view of what I mean of cargo capacity management. So you have on the upper here, you see the planning horizon, and we can focus on the right-hand side here first, which is the cargo capacity. So you can think about it, that capacity that is planned, say for a given day, or a given departure, if we're talking about air. So you can have any transportation mode, for instance, rail, truck, or air. Now, the focus is how do we use that capacity? And so there are essentially two processes related to that, the booking of that capacity. You have allotment contracts, which are negotiated on a more infrequent basis, and either it's like a bidding or negotiation process. So there you have the customers are reserving a capacity for a longer period of time at a fixed rate. And then you have the spot market, where booking request comes on a continuous basis, and these requests have different characteristics, such as when they are arriving, what is the weight and the volume of the requested. So for this shipment that they're requesting a booking for, what is the revenue, destination, and so forth. And then the carrier needs to accept or reject this decision. And there is some strategy around this, whether you are keeping capacity such that you have residual capacity to accept expected higher revenue requests that will come later. And the objective in all this is to maximize profit. So this is the revenue that you get from the request, subtracting the cost, which we will focus on in this talk in particular. So the cost associated with transporting this demand, and possibly some, cost associated with having an overbooking, so excess demand. And the exact problem description obviously depends on the scope, whether you're considering both allotments and spot market, if you're having a capacity defined by a network or just a single leg, and assumptions that you make about the uncertainty. But this is at a high level. So now we're going to focus on the spot market in particular. So I'm trying to give here just an illustrative example. So you will see at the bottom here, you have time. We consider discretized time horizon. And at the end of the horizon, you have some operational decision-making problem that you need to solve. So here we're considering a distribution logistics example, and this is also the application we consider later on. So it means that we need to solve a vehicle routing problem at the end of the horizon, VRP. Now, over time, you can get requests. Here we have the request J, which occur with the probability gamma, and they have associated revenue P. So you can see that the first request here is the red one, and it has a location in space that we can see at the end of the horizon. So if we accept the three requests that are exampled here, the red, the yellow, and the blue one, we all see that depending on where they are located, they will induce a different cost on the VRP solution. And this is the one that gives us the cost. So we can model this as a finite horizon markup decision process, where the decisions are simply whether we accept or reject each booking request that come. And the state is the number of accepted requests of each type before T. So any given time T, we have the state, which is denoted WT. And at the bottom here, I just write the Bellman equations, which are a very, very simple structure here, the value functions. And without getting into the details of those equations, what we really want to focus on here is that our end of horizon problem, so the one occurring at capital T plus 1 here, is actually our routing problem. And so it means that all our accept and reject decisions depend on the cost of this end of horizon problem. And this is a combinatorial optimization problem. So a few observations about the problem. I was just saying this end of the horizon is a combinatorial optimization problem. In the example that I had, this is a VRP, but it can be a multidimensional bin packing or both. It depends on the actual application. The MDP is typically intractable for any realistic setting because of the high dimensional state space. And this is true even for the passenger case, where you don't have this complicating combinatorial optimization problem at the end of the horizon. Now, what is important to note is actually when we're making the booking accept reject decisions, we're not really interested in the solution itself to the end of horizon problem, the operational decision-making problem. We're only interested in its value, right? So the cost of that solution. And so we're essentially here facing a booking control problem. So we need to have a policy for these accept reject decisions. We have imperfect information. So there is a stochastic setting, and we have very small computing time budget. Typically, these accept reject decisions need to be made online, real time, in a very short computing time. So how are these problems solved now, or what is the literature on these type of problems? So first of all, on the upper part here, you see what I refer to exact. So I'm just going, so we have our MDP formulation. And since we have these accept reject decisions, this leads to like threshold type of policies. So we accept the request if its revenue is greater than the expected opportunity cost of the capacity used by the request. So this is kind of the threshold type of policy that we will get. We can formulate this MDP formulation. So we can find a formulation for the optimal value functions, V, that we had, that I wrote on the previous slide. We can also write them as a linear programming formulation, which is used in several works. And this is nice because it provides any feasible solution will provide us an upper bound on the optimal value functions and also the upper bound on the optimal total expected profit. And so in the literature, what is kind of the most widely used are different types of what we call bid price policies. So this, which is this, you try to have an approximate threshold policy. And they are based, some of them are based on this linear programming formulation or actually reformulations thereof, because the MDP is intractable and the linear programming formulation is also intractable unless we're doing some approximations. So what is widely used is just to ignore the time dimension and to some extent also ignore stochasticity and formulate this as just one LP that gives us threshold policy and then re-optimize as often as our computing budget allows. So this is kind of what is most widely used in practice. For cargo capacity management in particular, I mentioned 2 lines of work here where we're considering dynamic bid price policy or dynamic, and also that depends on the capacity usage. So the idea there is essentially to take an idea from approximate dynamic programming. So instead of solving the LP for these value functions, we are replacing the value functions with the linear architecture instead. And then we kind of end up with much smaller LP formulations that we can solve. So these are the ideas from the literature, and obviously the case here, I'm ignoring a lot of the complicating factors associated with the end of horizon problem that are dealt with quite in neat ways in these works that I cite here. Now, I don't think I need to convince this audience about the literature of showing all the success with reinforcement learning algorithms for solving hard decision-making problems. Actually, it's not been so much used for revenue in the revenue management context, and the few works that we are at least aware about, they deal only with the passenger case. And what one can observe about almost all of these reinforcement learning algorithms and also some of the approximate dynamic programming algorithms are based on simulations of the systems, right? So you need to be able to simulate your system a large number of times. And then this end of horizon problem really complicates things. So simulation, if we need to solve this combinatorial optimization problem for each simulation, it becomes just prohibitively costly to do this simulation. So this is kind of so this is for the reinforcement learning comments. If we look at machine learning for heuristically solving combinatorial optimization problems, we've already seen several talks on this. There's a search of studies on this topic, great research coming out. There is the survey here by Benjo and others that I cite for an overview. Most of these are focused on deterministic problems. So we saw earlier, yesterday, the TSP talk on TSP. But most of those works are interested in actually solving, so replacing traditional OR algorithms by supervised or reinforcement learning algorithms. And they're interested in the fully detailed solutions. But actually, for our context here, we're not necessarily interested in the detailed solutions, we're interested in the value. And there are obvious synergies with the Q-learning, But there is also some of works that are interested in predicting just some characteristics of solutions. So Fischetti and Fraccaro showed that they can accurately predict values of solutions for a wind farm optimization problem. And we did some work here, Larsen et al., together to predict the description of solutions. So not the detailed solution, but some high-level characteristics of solutions to a second stage problem in a two-stage stochastic programming problem. And we do that with just supervised learning, which allows us to make fast predictions without even generating any scenarios, which is the typical way of solving this with sample average approximation over a certain number of scenarios. So that shows some success, and our reflex was that, well, actually, if we're only interested in the cost, this is a lot easier task to deal with. So this led us to this exploratory work, where the idea here is that we want to solve this booking control problem. We want to have a high quality policy, but at a very low online computing cost. And what we want to use is kind of benefit from the state-of-the-art reinforcement learning and approximate dynamic programming algorithms to solve this problem. And what we want to do in order to use the simulation-based methods, we want to use an approximation of this cost of the combinatorial optimization problem, which here we denote by gamma. And I'm just going to say that for right now, this is exploratory work, as I said, so we're going to use kind of off-the-shelf machine learning and reinforcement learning algorithms here. So what we're going to do is we're simply going to map our state space into a smaller dimensional feature space. So this is what I denote by the function g here. We have our approximation phi. So all now the v's that I had earlier, the value functions, and they all have a tilde now to denote that we're using an approximation. And the approximation is due to this phi approximation of the cost of the combinatorial optimization problem. Earlier we had gamma. So this phi could be anything, right? It could be a MIP solver that we call and we just collect the solution value. It could be solved heuristically, so just to a given time limit or optimality gap, or we can predict it by machine learning algorithm. And so we're going to focus here on when we view this as a supervised learning task. So essentially what we're doing is that we are separating now the problem of learning policy, so or this the booking control problem from the problem of predicting these costs gamma. And so we need to have data for learning this cost approximation. So we're doing offline data generation. And the aim is essentially that we want to have a good representation of possible end of horizon states, right? So these W t+1. So we're interested in obviously optimal, but also suboptimal states. So the way we're generating data now is quite simple. We're just assuming that we have a stationary random policy, so with a fixed acceptance probability, and we're just computing trajectories and collect our final state. And there we call the solver to give us the cost of that state. So this creates us a labeled data set. And we do this for an application to distribution logistics. So I already gave you in the introductory example, I already showed the distribution logistic example. So essentially, it means that you have this booking control problem, and at the end of the horizon, you have a VRP. So this is exactly the problem setting of the works of Giallombardo et al. So we're using exactly their same setting. And in this case, the booking requests are pickup activities. We assume that we have a fixed number of vehicles and the optimal value to the VRP is denoted by Z star here. That depends on the state and the number of vehicles that is used. And we assume that we only have K0 vehicles. So if we need more vehicles than that, which means that we would have excess demand, in that case, we incur an additional outsourcing cost that we denote here by C. So our operational cost, the gamma that I was talking about earlier, we have we have two components, two terms in that cost, our Z star and our C. So we're considering 4 sets of instances that vary with the number of locations that we're considering. So the size of the VRP, we're considering 4, 10, 15, and 50 locations. These instances are generated at random, and we're making sure here that the requests, the types of requests, they vary obviously with the locations and also the revenues that are associated with them, and we're fixing the probabilities such that higher revenue requests have a greater probability of occurring later in the booking period, so that it becomes interesting to have some strategic policy with respect to keeping capacity for later time periods. In terms of, so for the supervised learning part, when we want to, so that we do to learn how to predict these costs, we consider right now just a fixed input-output structure. So the output obviously is just one real valued number. That's why this is a simple task, or we expect it to be. And we're using a fixed input structures. We're just creating some aggregate features describing these instances.
Emma, you have 5 minutes left.
Yeah, okay.
Great.
And so we're computing, so we're separating the problem here of doing the cost approximation. So we're only predicting with machine learning the Z's, and then we're using a Bing packing solver, which is very fast, almost an instantaneous call, and we can get the outsourcing cost. So we're kind of separating the two. And we use fairly few instances for this problem. We're only needing about 2,000 instances, so 2,000 VRP problems here. And for training, and we use 500 here for our test. And for solving the booking control problem, we're using off-the-shelf reinforcement learning and approximate dynamic programming algorithms. So we have one which is just SARSA with the neural state approximation. It's an on-policy reinforcement learning algorithm. And then for the ADPs, we're using a rollout algorithm with Monte Carlo tree search. And we use 2 sets of simulated, for the simulation, 30 draws or 100 draws for each stage. And we will denote these SARSA, MCTS for the Monte Carlo T-search. And we have 2 different base policies. Either we just use a random policy with fixed acceptance rate, or we use SARSA, which is the RL1, but we use it as a base policy. And then we compare to the algorithms proposed in Gianlombardo et al., which are booking limit policies, threshold policies, very similar to the bid price policies that I described earlier. And for the very small instances, only 4 locations we included such that we can solve them with exact dynamic programming. So either calling the VRP solver when we're solving the DP, or just solving with the machine learning approximation. And we have also as a baseline just a stationary random policy. So we're evaluating of 50 realizations, and I just want to mention that for the machine learning task, we get fairly low mean squared errors and mean absolute errors, which confirms that this task is actually not a very hard one. And what we can see here is we look at the solution quality for only 4 locations. I'm showing here the gap to the best known solution on y-axis on all the diagrams that I'm going to show. And on the x-axis, you see the different algorithms. And what I want to point to here is that you see the DP exact and the DPML, they are very, very close, which means that this machine learning approximation, by predicting the end of a rising cost, does not seem to incur any poor solutions. So it seems to work well. And we can also see all the ADP and RL algorithms have fairly good accuracy and outperform the baselines, which are shown in orange. Now we're switching to 10 locations, and what we can see, it's still the performance of these RL algorithms and the Monte Carlo tree search ones are fairly good, still the gap to the best known solution on the y-axis, and they outperform here our booking limit policies and the random one. So now we're going to focus just on the evaluation of these RL algorithms and the Monte Carlo tree search ones. So for 15 and 50 locations, we're seeing the similar picture. Actually, as expected, the Monte Carlo tree search algorithms perform the best. And when we increase the number of simulations, obviously our variance go down. But actually, for the largest instances of 50 locations, SARSA is performing quite well. And that is interesting because when we now turn our attention to the computing time, which is my last real slide here, is that SARSA is extremely fast online computing time, right? So less than 2 seconds to get our to solve these on average these instances, whereas the rollout algorithms are completely online algorithms, so they have no offline computing time, is what you see in gray, and the online is in green. And here we can see that they are considerably longer. So for the largest instances, they are almost 4.9 minutes with the random based policy and 7.5 minutes for SARSA when we're doing 100 simulations. So it's considerably longer than SARSA alone, which takes on average less than 2 seconds. And if we look at the baselines, the bid booking limit policies, they are fast online computing times, but also quite poor quality. So the idea here was to use machine learning to predict solution cost to this combinatorial optimization problem that is really the bottleneck in existing solution approaches. And now when we do that, it opens up the possibility to use state-of-the-art reinforcement learning and ADP algorithms. And here in this exploratory work, we just used off-the-shelf algorithms. But obviously, next steps for future work is to go beyond off-the-shelf RL algorithms. And we're also working on a second application to airline cargo capacity management. So I just want to flash this slide since it's recorded to give the references, and I'm happy to take any questions.